Chapter 2 gives us an introduction to chemistry. Now, this is not going to be very involved chemistry. We are going to introduce or review some of the basic chemistry ideas so that we can understand how biological molecules are put together. So we're not going to go very in depth. We're just going to cover enough chemistry so that we can understand how living things are put together. So as we go through chapter 2, yes, this is a biology class. Yes, biology is the study of life. However, we have to spend some time studying chemistry and studying physics because, believe it or not, living organisms and the environments that they live in are still subject to the basic laws of physics and chemistry. And so to understand how living things work, we have to understand a little bit about physics and kind of a lot about chemistry. So we're going to start pretty basic. Key concepts for this chapter are going to include a discussion of matter. So we're going to be talking about elements and their compounds. And we're going to talk about elemental properties. How does an element get the characteristics that it gets? We're going to hopefully understand by the end of the chapter that this all comes from atomic structure. Once we have that foundation, we're going to talk about formation and function of molecules and how this depends on chemical bonding between atoms. And then we're also at the very end going to take a very quick look at chemical reactions, this making and breaking of chemical bonds between atoms. Okay, so let's start basic. Organisms are composed of matter. What is matter? Simply put, matter is going to be anything that takes up space and has mass. So it's stuff, right? So organisms are made out of matter, but also the environment that we live in. Everything around us is made out of matter. Now, if we were to get a little bit more scientific, matter is really made out of elements. And the way that we define an element is that it is a substance that cannot be broken down to other substances by simple chemical reactions, right? So it's kind of the purest of the pure. You can, however, take elements and put them together in a given ratio. And when you do this, you create what are called compounds. So a compound is defined as a substance that consists of two or more elements in a fixed ratio. Let's take a look at an example. So the example that we have down below shown in images. The very first image, you see somebody cutting a grayish brick with a knife. This material, that gray material, is actually sodium. It's a metal. It's a very soft metal. You can cut it with a knife. I don't know if anybody has ever seen this, but if you haven't, Google it. Google what happens to sodium when you put it just in water, right? Most things might float or dissolve, kind of boring, right? But when you put sodium into water, it actually ignites, it combusts this bright blue-white flame. And so it's highly reactive in something as benign as water. The other element here in the round flask is yellow gas. This is chlorine gas. It's actually toxic. It's poisonous. So you've got one element that's a metal that blows up in water, and you've got another element, a gas, that is toxic, right? You put these two things together in a 1-to-1 ratio, so one chlorine, one sodium, and you create table salt. You create sodium chloride, something that we ingest on a daily basis as Americans probably way too much of. It doesn't harm us, right? It doesn't explode. It doesn't kill us. It's very tasty. And so this is a great example where you have an emergent property arise, right? You've got two elements that on their own have two very different properties, but when you put them together, you form a compound. Now this compound has a new set of characteristics, new emerging properties. Now, we're going to get a chance to look at the periodic table of elements. We're going to get a chance to learn how to read it, understand some of the patterns that are found within the periodic table, but we're not really going to cover all elements in the periodic table of elements. And this is because they're not all necessary for living organisms to survive and be able to reproduce. In fact, there are only about 20 to 25% of the 92 elements that are thought to be what we call essential elements, meaning those elements are necessary for living organisms to survive, to thrive, and to reproduce. Now, there's a little bit of discrepancy there. It's not just one set number of elements, because different organisms, plants versus animals, for example, will need different elements more or less than the other. But because we're humans, let's focus on humans. So this table shows you elements that are found in the human body, and it's kind of divided up into 3 sections. So the top section, you have those elements that are most commonly found in the human body. These are the elements that make up about 96%, almost 97% of who you are. This is oxygen, carbon, hydrogen, and nitrogen. Below that, we've got another chunk that makes up the remaining 4-ish% of your body. And these are elements like calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. Right, and when you hear some of those, you can kind of imagine where they might be useful, right? Calcium, potassium, bones, muscles, magnesium, for example. These are elements necessary for various parts of your body to function properly. And then we've got at the bottom what are called trace elements. Now, these guys are necessary, but only in very minute quantities. So my favorite letter is letter I. Let's talk about the 2 elements here in the trace elements box that begin with the letter I. So we've got iodine and we have iron. Iron, hopefully somewhere in your education you learned that iron is important in your red blood cells. Right? Iron is used within a protein in your red blood cells. It's called hemoglobin. So this protein, hemoglobin, has an iron atom, actually 4 of them, in the structure of the protein. And it's the iron that helps to attract oxygen to the hemoglobin so that your red blood cells can hold on to that oxygen and carry it to various parts of your body so that your cells have the necessary oxygen to go through cellular respiration to be able to thrive and survive. So you need iron. Iodine, this one's a little bit more tricky unless you're familiar with the thyroid gland. So your thyroid gland produces a hormone that's called thyroid hormone. And to make it, your thyroid gland needs iodine. If you don't have sufficient amounts of iodine in your diet, then you will have a malfunctioning thyroid and it will grow in size and it'll create a big lump underneath your chin. It's called a goiter. So it's important that we have enough iodine in our diets. We don't need a lot, but good sources would be things like seaweed. I don't know about you, but I don't eat seaweed on a daily basis. So what we've done is we've actually combined iodine with table salt. Have you ever gone to the store and you've bought salt? There are lots of options from sea salt to kosher salt. Well, there's also iodized salt. This means that it has iodine added to it. And again, goodness knows we eat a lot of salt. And so this ensures that we also get the necessary iodine in our diet for a fully, normally functioning thyroid. All right, so I don't want you guys to memorize this table. However, you will get a chance to learn those first 4 elements, the ones that make up the most of your body. This is because the molecules that make up your cells make up your body. Those molecules are primarily just made out of oxygen, carbon, hydrogen, and nitrogen. And we'll get a chance to look a little bit more into that in chapter 4. Okay, so let's talk about these elements. Each element consists of unique atoms, right? That's the substance an element is made out of, atoms. How do we describe an atom? An atom is the smallest unit of matter that still retains the properties of that element. So that means, yeah, you can break an atom down further, but that atom is no longer that element. It's lost all of those properties that the complete atom had. I like to think of an atom in chemistry being the same thing as a cell in biology, right? We talked about how the cell is the lowest level of biological organization that still maintains all those properties of life that we talked about. Sure, you can break it down further, but those individual smaller components are no longer considered living, right? You need the full cell. So this is kind of the same thing here, right? You've got an atom, yes, you can break it down into smaller pieces, but it doesn't retain the properties of that original element anymore. Regardless, let's talk about what atoms are actually made out of. So they're made out of subatomic particles. There are lots of different kinds. We're going to focus on 3, the major players. So neutrons, first type of subatomic particle. These, as their name implies, are neutral, no charge. Protons, these have a positive charge. And then you've got electrons, and electrons carry a single negative charge. So neutral, neutrons, positive protons, and then negative electrons. Next, we need to talk about, well, how are these subatomic particles actually organized within the structure of an atom? So the neutrons and the protons, the positively charged particles and the neutral particles, cluster together in the very center of the atom, forming what is called the atomic nucleus. So here in this case, you see an example of a helium atom. In this helium atom, you've got the 2 positively charged pink protons and the 2 brown neutrons in the center there of the atom. That's your atomic nucleus. The electrons are tiny particles, and they are buzzing around this atomic nucleus in a cloud. Now, there are 2 ways that your textbook and many other texts like to represent atoms. You can either look at it in the figure on the left. In this case, you see the atomic nucleus, and then you see a yellow cloud. That yellow cloud implies that there are electrons buzzing in there really, really fast, but you can't really pinpoint where an electron is at any given time, but it's in that cloud somewhere. Maybe a little bit easier to visualize. On the right-hand side, we have a depiction of an atom where you have, yes, the atomic nucleus in the center, and then the electrons look like they are orbiting around the atomic nucleus, kind of like in space, right? You've got the sun in the middle, and then all of our planets are going to be orbiting around our sun.